In this video, I want to try to extend the idea of Maclaurin series out to a more general version known as Taylor series. Taylor series, you're basically writing a non-polynomial function as a polynomial function, but it doesn't have to be centered at 0. It can be centered at any value. We usually say that it's centered at some x equals c. So it might be centered at 1, or it might be centered at 5, or something like that. So in a minute, I'd like to write a Taylor series for the sine function centered at x equals 1. Before I do that, though, I want to generalize what we saw with the Maclaurin series because there's some important patterns here. So if you remember, I took the function value at 0 had to be equal to my series value at 0 had to be equal to the function value at 0, and my series first derivative at 0 had to be equal to the series first derivative at 0, and my function second derivative at 0 had to be equal to the series second derivative at 0, and so on and so forth. So I've listed first, second, third derivatives up here. And I just made the point here that so if the functional value at 0 had to be the same for the e to the x and for the series, I would have 1 c naught. Of course, you're dividing both sides by 1 here. And remember that that 1 was actually a 0 factorial. Okay, so you could say that c naught was really, this is going to be the coefficient of the x term, right? You could really say that it's the functional value at 0 divided by 0 factorial, okay? And then for the first derivative term, for the c sub 1 term, I, again, have 1 to c sub 1. When you substitute 0 in up here, you're just left with this equal to the first derivative at 0. And so you can divide both sides by 1. And that 1 there, to knock out that 1 was really 1 factorial. So you're taking the functional value at 0 divided by 0 factorial to find c sub 0. To find c sub 1, you're taking the functional value at 0 divided by 1 factorial. Okay? For the second derivative value, you're going to have 1 times 2, which is 2 factorial c sub 2. Everything else is going to cancel out here. So that's 2 factorial times c sub 2 equals the second derivative at 0. We can divide both sides by 2 factorial, and you can see here that c sub 2 is going to be equal to the second derivative divided by 2 factorial. And this pattern continues. The third coefficient, c sub 3, is going to be equal to the third derivative at 0 over 3 factorial, and so on. And what you can see here is there's actually a pattern for how you can generate each of these coefficients without having to write this entire series out every single time and taking the derivatives and second derivatives and third derivatives and so on. And that is that the nth term is always the nth derivative of the function. So the c sub 1 term, it's the first derivative at 0 divided by 1 factorial. The second term, c sub 2, second derivative divided by 2 factorial. Third term, third derivative at 0 divided by 3 factorial. It's the nth derivative, okay? We would call that the 0th derivative, right? You're not taking a derivative, it's just the functional value, okay? By the way, a term that they'll use here, if you're taking like a 6th derivative or something like that, you're not going to keep putting tick marks there forever. So they'll actually do something like this, like a 4th derivative. Yes, I could do f quadruple prime, but you could also just do f with the little 4 there, basically just saying a 4th derivative. So what we're really doing here is we're taking the nth derivative at 0 and we're dividing by n factorial. That's the coefficient, okay? That would be c sub n, basically. And then, of course, if you wanted to find any individual term of this series, it would be multiplied by x to the n. And then, of course, if you wanted to generate a formula for the entire series, you could say this is the sum from n equals 0 to infinity. Okay, that is the formula to generate a Maclaurin series, okay? Now, typically with Maclaurin series, we have these kind of known ones, like the sine function and cosine and e to the x and all of that, and so you may not have to use that definition a whole lot. However, this can be generalized, and this can be extended out to a Taylor polynomial for a function that's centered at some value that's not 0, okay? And the idea here is very similar to this. The big difference here is it's going to be shifted to the left or to the right. Okay, so for example, I want to write a sine function centered at 1. Okay, think about parabolas for a minute. If I had y equals x squared, I wanted to shift it 1 to the right, I would do y equals x minus 1 squared. Okay, if I wanted to shift this parabola 2 units to the right, I would do x minus 2 squared. Okay, what's going to end up happening here is this function is going to be shifted c units to the right. Okay, so you're going to have an x minus c inside parentheses to shift it sideways. Okay, so the basic formula here, instead of being, well, it's still going to be c naught, but then you'll have a c sub 1, and instead of c sub 1 x, it's going to be x minus c. Okay, and instead of a c sub 2 x squared, it's going to be an x minus c squared. Okay, and instead of a c sub 3 x cubed, it's going to be x minus c cubed. Okay, and what's going to happen, by the way, like, for example, if we're centered at 1, that means that c value would be 1 each time. If you sub in 1 to the function, each of these is going to end up being 0, and everything is going to cancel just like they did before. Okay, and then the other thing that will happen is, remember, we were taking the nth derivative at 0, and we were dividing by the factorial. In other words, we were finding the first derivative slope at 0, the second derivative slope at 0, the third derivative slope at 0. And we were getting all those to match up. If we're going to center it at 1 or at 7 or at -6, we need to make sure that we're taking the derivatives at those values. So I'm not going to take the derivative at 0 anymore. If I'm going to center the function at 1, I would take the derivative at 1. Okay, so we're going to tweak this formula just slightly. For a Taylor series, we're going to take this formula and generalize it. Instead of x to the n power, we're going to have x minus c to the n power. Okay? And the other thing here is we will no longer be taking the nth derivative at 0. We're going to take the nth derivative at whatever value our center is. Okay? So it's just a slightly tweaked formula here, taking the derivative at the point that we're using as our center and shifting it over however many units we want our center to be located at. Okay? And so, let's come back to this. If I want to write a Taylor series for the sine function centered at x equals 1, again, we can really just use the formula to crank out these coefficients here. It's always the nth derivative at our center divided by n factorial. We can crank that out very quickly. Okay, so for the sine function here, let's try this. So c sub 0 would be the 0th derivative at 1, okay, in other words, sine of 1, divided by n factorial, which is going to be 0 factorial, okay? Well, the 0th derivative is just the functional value at 1, okay? So I'm going to take the functional value at 1. The functional value at 1 is just sine of 1, okay? I could evaluate that I could get a decimal. I don't want to do rounding in this, okay? I want to keep this in exact form. So it's going to be sine of 1 divided by 0 factorial. And then, of course, we're multiplying by x minus 1. And this is the 0th term, so it'd be the 0th power. So that'll, of course, just become 1 and go away. So it's going to be sine of 1 plus, then we're going to take the first derivative at 1 divided by 1 factorial, and we're going to have x minus 1 to the first power. Okay, well, the derivative of the sine function, f prime of x, would be equal to cosine of x, right? So the first derivative at 1 is going to be cosine of 1, okay, divided by n factorial, which is going to be 1 factorial, so it's just going to be over 1. And it's going to be times x minus 1 to the first power, okay? And then we can continue this, okay? The coefficient of the second term will be the second derivative at 1 over 2 factorial. And then we'll be taking this to the second power for the variable, okay? So the second derivative is going to be negative sine of x, okay? So that would be negative sine of 1 is our leading coefficient. You're going to have an x minus 1 squared. And again, this is the second term, so it's going to be over 2 factorial. okay? And then we can continue. The third derivative at x is going to be negative cosine of x, okay? So we're going to take the third derivative at 1 divided by 3 factorial times x minus 1 to the third power, okay? Third derivative at 1 is going to be negative cosine of 1, so it would be minus cosine of 1 over 3 factorial, that's our coefficient, and then we're going to have an x minus 1 cubed, okay? And if you graphed this series, if you typed in just this many terms, and you took a look at the function we're trying to model, which is the sine function, okay, and you looked at values near 1, type this into Desmos, okay, make sure you're in, you know, radian mode, I suppose. But anyway, type the sine function in, and then type in the first 4 terms of this series, okay? And you will see that near 1, the function value will be the same, the curvature will be the same. As you get farther away from 1, that won't become as good, okay? For people in the 2020 class, I've linked a Khan Academy video. The second half of that video, I think he does cosine of 1, and he shows how closely it matches up, and it's really cool as you continue to add terms to see that it conforms more and more closely as you get more of those derivatives matched up. Okay, so that's the idea of generating a Taylor series centered at a certain point. This formula is unbelievably important. I cannot stress how important this is. It's the nth derivative at the center over n factorial. That's always times x minus c to whatever power the term is. Okay, we're going to have to continue to build on this, but that's a pretty good starting point.